Hello, you're welcome. You're welcome back to. Yeah. Okay. Anyway, I was talking about wine analysis, and they were merged together, and their distributions were discussed. So I want to show you some significant things here. Already there are sort of distributions. Um, Actually, there are so many distributions regarding these continuous random variables. We have to talk about PDFs, probability density functions, right? So in order to study it, first of all, I'm going to load these histograms. They can be done with the help of hist function. That's a default function in R programming. I'm going to use a for loop because we have a couple of columns. We have 12 much of columns to be studied. So I'm gonna use this inside for loop as usual. Other languages, hist. So wine square bracket with a comma, which means that we leave a space there because all rows may be considered, but we have to consider this much of columns over there, right? Okay, now you can see all these histograms are being prepared, right? Let me show you like this, but it's a little bit difficult to identify whatever the variable um, is this. So let me set these variable names. Call name, call names. Names function, that's the default function in R. Names function wine I then main equals call name, right? Okay, now it's much more convenient to study these, right? Because they are executed with their own attribution, own column names. It's like this. So I'm not going to talk about each of your variables, but I will pick um, only a few variables like this. What is this? Residual sugar. This residual sugar seems like an exponential distribution. So I used to plot this density with the help of ggplot2, right? ggplot2. Let me do it. Complete ggplot data equals wine geom density mapping equals aesthetic x equals what residual sugar wine dollars residual sugar, and this is not needed. You can drop it. I used to fill it with color. Fill equals blue. Okay, let's see whether that's seems like something exponential or something different, because this is the tends up to the real scenario, right? Tends up to the real scenario rather than studying residual sugar. What do you think? Residual sugar. Residual sugar. Let's take a look at this. this. This is volatile acidity. This is citric acid, residual sugar, chlorides, chlorides, residual sugar, chlorides, chlorides, residual sugar. Right, right. I think it's better to talk about residual sugar. You can talk about any, but I'll explain based on residual sugar. It seems like an exponential probability density function. So I assume that this is an exponential, but actually this must be discussed based on subjecting gamma distribution. This is pretty close to gamma distribution. We have two branches under gamma distribution. There are two edges. One of that is just chi-square chi distribution, and the other one is nothing else, exponential distribution. So this is an intermediate one. So the actual scenario tends up to a gamma distribution with significant alpha value, so we want to find it out. In advance, I'll talk about exponential distribution. I'll assume that this is distributed as an exponential PDF, right? So with that assumption, in order to find out the distribution, what are the parameters we want to find out, lambda, right? I think it's better to have a look at exponential probability distribution. Once the random variable is larger than 0, this is executed, right? Lambda times e to the power minus lambda x, right? So this is what we are focusing on. We assume that this distribution follows up this type of shape, right? Okay, assuming that we know when we compute expected value of the random variable, we can get it. It's nothing else, it's just the arithmetic mean of all these continuous random variables. It's going to be equal to what? 1 over lambda. It's nothing else, just 1 over lambda, right? And variance of the random variable is given by 1 over lambda squared, and the standard deviation becomes 1 over lambda, right? Okay, so in order to find out lambda is the parameter which is much more important to read this exponential distribution. We can interpret this exponential distribution after immediately finding out lambda, right? Okay, so I'm going to work out of lambda, right? Okay, lambda, lambda, according to the PDF, lambda is going to be equal to 1 over yeah, expected value of the random variable is going to be equal to 1 over lambda, then lambda is going to be equal to the upside down of expected value of the random variable. How we can write it with the help of the default function in R, mean, what we have taken, mean of what? Mean of residual sugar, right? Okay. Now let's see. Paste lambda of exponential PDF is lambda. Let me print it. Even you could use just print, right? Lambda of yeah, this is lambda, right? This is lambda. This is what we found out. If it is true, let me check. Actually, we assume that this is following up an exponential probability density function. It tends up to that type of function, but that's not the realistic, right? It's pretty close to that type of function. So we are looking for the best fitted one, right? We can never find out the best one. We can find out a tendency. We can find out a tendency, right? Somehow, it's the standard deviation of wine residual sugar must be pretty close to 1 over lambda, because variance of the random variable is given by 1 over lambda square. Then when we get the square root of that, it must be equal to the standard deviation, right? Then 1 over lambda, right? Okay, let's see. Um, there is a difference between standard deviation and 1 over lambda. Um, there is a difference. Actually, we have assumed. There is a deviation. So we assume that, right? Okay. Based on this assumption, you can see how far it is fell. If they are pretty close, we can let's say fairly can be said that this is with an exponential probability distribution. Somehow, I'm depending on the assumption furthermore, and I'm gonna show you um, one more thing, right? How to how to plot this prepared probability distribution, right? Uh, PD is gonna be prepared, right? With the help of let me call it XPDF, right? XPDF. Then let me call it exponential probability distribution. I'm gonna use tuple. This is a function which is executed under dplyr library. That's a versatile library, right? So uh, I'm trying to use that library to plot my desired function, plot my uh, prepared function distribution, probability distribution, right? Then y equals, lambda times e to the power exp, right? Exp minus lambda times x, right? Okay, x is prepared in between 1 and 100, because in our random variable it is spread out in between. Yeah. Somehow, while it is turned into a probability density function, it must be spread out in between 0 and plus infinity. So that's how we will read the exponential density function, right? Okay. So that's the piecewise function, right? So otherwise it's zero. Otherwise the probability density is just zero, right? Okay, probability density does not equal to the probability. Once we find out the area under the curve and the particular region, the particular range, we can find out the probability for the desired moment, right? Okay, somehow I think you are familiar with that, with those theorems. So um, I'm gonna show you XPD, right? Exponential probability density function is going to be shown. Okay, this is what we prepared, right? These are x values and these are y values, corresponding y values. So I wanna plot it. I use ggplot, or even that can be done with no help of ggplot. Just you can use plot um, plot xpdf against x, right? xpdf y. Let's see. xp pdf. That's why it's not working, right? Okay, now it should work, right? It's like this. It's like this, right? Nice. It can be interpreted with the help of ggplot2. Let me do it. ggplot data equals xpdf pdf XP PDF, right? XP PDF. Oh, geo. What we need? What we need? Geo line. I need geo line, right? Okay. Then mapping aesthetics. X equals x and y equals y. It's nothing else, right? Okay, now I'm gonna plot it, and I wanna add one more thing. What is it? So I wanna add one more thing. What is it? What is it? What is it? It's nothing else. It's mean, right? Uh, mean of what? Mean of what? Random variable. Yeah. Let's add um, geo vertical line. Have I started recording? Yeah, okay. It's been recorded. This I wanted to make sure. Oh, otherwise I'll be trapped in the huge trap. Right. I have to do it again. So V line. V line. Okay. X intercept. X intercept equals mean of one, mean of uh, mean of wine. We are working on residual sugar, right? Okay. Um, let's check whether it's working or not. It should work. It should work. Let me change the color of this. Uh, color equals red, right? Okay. So this is the prepared exponential distribution fitted with this one. You can see there are some deviations. There are some deviations. You can compare it with this one, right? Let me add the same plus geo v line x intercept mean of what wine or residual sugar, right? Color equals red. It's too easy, right? Okay. Now let's try to compare it. Mean is nothing else. It's here. It's approximately. What is the corresponding y value? What is the corresponding probability density at that moment? 0.05. Yeah, 0.05. It's pretty close to 0.05, but it is not 0.05 yet, because you can see there is a drop. There is a drop here. There is a deviation from that exponential distribution what we have for, because actually we have received, but I think it's better to model this probability density function as a gamma distribution. I'll show you how the gamma distribution will be look like, right? So let me do it. Gamma distribution. I'm talking about gamma probability distribution. The gamma distribution is a nice distribution. We're talking about positively skewed distribution. You can see this is a positively skewed distribution. As I mentioned earlier, there are two major types. There are two ending points, two boundaries, right? On this side, there is chi-square distribution. On my right-hand side, there is exponential distribution. It's based on this parameter. Additionally, there is another parameter as alpha, right? Lambda to the power alpha, like my earlier case, there is lambda e to the power minus x times x is nothing else, that's just the random variable, times x to the power alpha minus 1 over gamma, right? I think now at this moment you must be familiar with gamma distribution. Gamma distribution is a very fantastic distribution, just like pi distribution, pi function. This is on the denominator you can see gamma of alpha, right? Gamma of alpha is nothing else factorial of alpha minus 1 factorial, right? It will be given by integral from 0 to infinity t to the power x minus 1 times e to the power minus t by dt. It's going to be equal to gamma of x, right? So when we simplify that, it becomes x minus 1 factorial. Likewise, this becomes alpha minus 1 factorial. Right, okay. Uh, I'll show you it later, but I don't think this is not time to explain those mathematical parts here. I'll do it distinctly. Make sure I'll do it for you, right? But here I want to show you the importance of this gamma distribution. In this case, fairly, it's talking about those intermediate positions in between chi distribution and the exponential distribution. So how far it is skewed, how far it is positively skewed. It's explained by gamma distribution. So once alpha equals one, you can see we can find out lambda to the power 1, right? E to the power minus x lambda, right? Minus x lambda, x to the power alpha becomes 1, x to the power 0 becomes just 1, right? Over gamma of 0, gamma of 1. Gamma of 1 becomes factorial 0. Factorial 0 is nothing else, just 1, right? So it becomes the exponential function. Once alpha equals 1, it becomes the exponential probability density function. So in my earlier case, I was working on that. If you have worked on this gamma distribution, you can realize that the expectation of the random variable becomes alpha over lambda, right? Alpha over lambda, and the variance of the random variable becomes alpha over lambda square. Then when you get the quotient between those two, you can find out lambda, hence you can find out alpha. So in order to model this distribution as a gamma distribution, there is an additional parameter. Um, so we have to find out alpha as well. Then with the help of alpha, we can um, let it be let it pretty close to this distribution. So likewise, we can do we can work on others too, but you should know you should have a proper knowledge about all the other distributions what we are having. As I said earlier, binomial, there could be binomial, but in our case, we don't have any binomial case except red and white lines, right? So I hope to do so many things here, right? Yeah, okay. I think it's better to model this function. Yeah. Okay. Alpha over lambda equals the expectation, right? Then uh, alpha over lambda square equals the variance, right? Variance. When we get the quotient, it becomes lambda, right? Hence, you can find out lambda. Then by substituting on this on any of that equation, you can find out alpha. So likewise, you can prepare the distribution like this with the help of table function, as I did, right, for the earlier one. So I think I'll let you do it yourself. We have so many things to do. right? We have so many things to do. Uh, like I'm gonna may do some predictions, right? I'm gonna let you go through some classification models in data science, in machine learning, right? Um, so, right, okay. I think it's time to show you some scatters, how we can interpret some scatters, right? Mm, and some correlations. Correlation, Pearson correlation coefficient. There are some more correlation coefficients, but for numerical variables, we are working on Pearson correlation coefficient. In our mathematical model, you know how they are correlated, how two variables are correlated. It is linearly explained how a variable is explained by another variable linearly. It is indicated by correlation coefficient. So it's between 1 and minus 1. So if it is pretty close to 1, if it is larger rather than if it is larger than 0.8, we can say it's a strongly positively correlated. Those two variables are positively correlated. Then there is a strong linear correlation. So we can do it with the help of functions. Um, in R, there is a inbuilt function. Otherwise, we have to write down codes for each of every computations. No need to worry about that because of these functions, right? Okay, I'm gonna use library coplot, right? This will help me to interpret this nicely with the help of coplot. Um, you can see it nicely. Let me show you how we can do it. Coplot, coplot, coplot. Inside that correlation. Sorry, just inside parentheses. We need wine, but numerical values only. Wine. Let's apply. I'm going to filter only numerical values. What's my dataset? Wine. Here function I need only is dot numeric. I need only numeric values, right? Okay. Let me show you how it's working now. Right. It's like this. If you want to show only um, type equals num, right? No. Type type means upper or lower. We need upper one, right? Because it is symmetric. We need only upper one. Method. Uh, most of the guys they think that the method means Pearson or Spearman or something like that. No, in this library, in this function, the method is just the number or it can be interpreted with circles and the color intensity. So here I use method as number, right? There will be correlation coefficients, right? Okay, you can see there is a negative correlation between density and alcohol. It's a negative correlation, but it is not explained linearly too much, right? But still, all the other correlation coefficients are pretty small, right? Um, Around 0.5, and most of them are less than 0.5. It doesn't mean that there is no relation. It means that they are not explained linearly. They are not explained linearly. There can be a relationship as a sinusoidal following up cubic or or any other exponential, logarithm. There are so many relationships. Even there can be polynomial, rational, so harmonic, homogeneous. There can be so many, right? So there are some techniques to find out whatever the relation they are existing. So in this session, I am not going to talk about everything, but here I want to talk about one more thing. I'm gonna tell you one more thing in in machine learning. When we study a data set, right? We are gathering so many data. Infinitely, we can gather data, right? Infinitely, we can gather data. Uh, then the population can be gathered infinitely around us. We can never stop by collecting this data, but this is a sample, right? According to statistics, we consider that if it contains only equal or less than 30 elements, 30 objects, it is considered as a sample, and otherwise it's a population, right? Uh, so it's likewise. But here, I see that we can never stop collecting this data. So it's still this is a sample, right? Still is a sample. We can never acquire the population. So in the statistic theory solution, we can use combinations. We can use combinations to simulate so many samples. That's a technique in statistics where we can find out the relationship between sample and the population, right? Okay, I'm not gonna go you with some theoretical parts. Just I want to let you know, convey the idea what we are doing here, why we are doing here. So to understand that, we should know some more idea about the background of statistics and probability as well. It's very significant. It's very important, right? Okay. Somehow here, when we prepare a model, okay, I will say correctly. I'm gonna I'm gonna create a model to predict whether that's red wine or white wine. It's important. At the rest of this session, I will show you. I'll show you what's the importance of that, right? With some experiments, right? I hope to share some experiments with you, and how we can make sure whether this model is a fine one, or it's whether it's working properly or not, right? How we can measure the accuracy, right? Okay. The solution is we are having this data set. We cannot find out some more data at this moment, right? So with my existing dataset, I'm gonna split this dataset into two parts. One part is prepared for the training data. By going through those training data, we will train the dataset. We will train the dataset means we will prepare our model based on that data set, right? Comparatively, it must be with a higher amount, right? 80%, or sometimes we will take 75%, or 25% will be uh, kept as the testing set, right? So that remaining set will be used for testing this model. Testing means we can find out the accuracy. We can evaluate this model, right? That's the purpose of this splitting, right? Okay, so there are so many methods to split it using R. I'm gonna use CA tool today, right? When I do some more analysis, I hope to do some more things here. Uh, I have some idea to collect data on vehicles in Sri Lanka, and selling prices and buying prices, and others, some more things considering especially um, market, right? So it will be a market study of vehicles in under current situation, under current policies and political background. So in that case, in those cases, I will use some more different methods to do the same, right? Okay, today I am gonna use library CA tool, right? CA tools. Okay, somehow um, but or something else. You can name it with your own idea, right? Sample dot split sample.split wine any variable in your dataset wine split ratio my split ratio is 0.8, right? Then 80% of my dataset will be put into training data, right? Normally we use a huge amount of data. Portion will be used for training the model. Other remaining part will be used for testing the model, right? That's the usual way, right? You can switch it, but this is the proper way, right? If you are available for collecting some more data considering the same sample, even you can use all this data for training the set, and new data can be used for testing the model, right? uh, Train, I'll call this training set as train now wine include part part all the columns will be included. Test, right? Testing set, test, wine, square bracket, not equal parts. It stands for not equal, right? For expressing not equal, right? Okay. I want to make sure whether it's split properly or not. So dimensions will be checked. Dimension of train, and dimension of test. Right, okay, let's see. Let me run it. Right, okay. I don't remember exactly how many data was there, or even you can check it. Dimension, dimension of wine, right? Okay. So when you run your code multiple times, this splitting, these are done randomly, right? These columns are picked randomly. So this combination will be changed because the samples will be split randomly. Then when you load your when you run your script first time and second time and the third time, they will be different. There is a you can see there is a the output will be different, right? Because of this randomization. When you try to run your code multiple times, your randomization will be changed. But still, our command is to split this data set into two parts with this split ratio. It will be preserved, but these rows will be changed, right? So rows will be changed. So in this analysis we want to make it constant for nothing else. Just we want to based on fixed scenario in this analysis. It's nothing else, right? So set dot seed, I'll use my lucky number, right? It's my lucky number. Okay, right. So dimension one, you can see the summation of these two dimensions is going to be equal to the total data set what I had prepared earlier. There are 30 number of columns. So this is the starting moment, right? So next time I'll show you how to prepare a binary logistic regression with the help of this dataset. With the help of that model, we can predict nicely whether this is whether a wine is red or white um, once we are given all these attributes. Right? Okay. So I'll not stop it by that. I'll show you how to do the same with the help of some more different machine learning models. There are some algorithms, it's like clustering models and classification models, especially uh, k nearest neighbor classification, right? And there are some more clustering models, k means clustering, and some more things, right? Right, okay. For now, I'll stop it by here. Hope you could understand, you could get a better idea about all these. If I have made something issue, no need to hesitate, just you can let me know, right? Okay. Uh, so it's time for a while. Okay. Thank you.